Hello, my name is Hannah Momsen.
And I'm Teresa Gannon.
We are here to present the knowledge we have gained from the immersive Assembling San Francisco, in which we explored the geological structures of this area and how they were created.
To begin a conversation about San Francisco's geological history, first we must travel back to the Precambrian era, 4.5 billion years ago, when the event known as the Big Bang occurred. During this time, Earth as we know it today was created, even though everything looked a bit different. Fast forward 1.3 billion years, and we see what scientists believe to have been the beginning of modern plate tectonics, though they may have taken up to 1 billion years to form through a process similar to subduction. Subduction is the process of one tectonic plate being pulled beneath another due to differences in densities, which happened even before plates were defined in the ways they are today. In this time, parts of the crust were being pulled into the mantle while weakening other parts, creating boundaries that eventually were distinct enough to divide the Earth into tectonic plates. Pangaea, the supercontinent that all our current landmasses came from, formed in the Mississippian era about 335 million years ago, and began to break apart in the late Paleozoic and early Mesozoic eras, approximately 175 million years ago. All of this led up to North America becoming its own continent, with a plate individually responsible for all of our boundaries with other plates and the effects they have on us, particularly in San Francisco, even though at that time the Bay Area had not yet come to be.
Though we do not know for sure what the cause of tectonic plate movement is, most geologists today believe Arthur Holmes's 1928-29 convection current theory. This theory explains the motion of plates according to the currents of the magma beneath it. As Earth's core is extremely hot, the magma closest to it is heated up and rises towards the crust. Once the magma gets to the top, it's further from the core, so it cools down. The cooler magma is denser, so it falls back towards the core, where it heats up again. This creates a cycle. Beneath the crust, there are many different sections where magma is undergoing this cycle. Each of these sections are called convection cells. Among the cells, magma moves in different directions and causes the difference in plate movement. At the beginning of modern plate tectonics, Pangaea was ripped apart into 7 continents that we know today. The North American continent, where San Francisco would one day be, was pushed west as the Atlantic Ocean was created. It kept moving until the North American plate collided with the Farallon plate, and they pushed against each other. The Farallon plate was less dense than the North American, so it began to subduct beneath it. This was how San Francisco got many of its types of rocks as they were accreted onto the continent. Accretion is the process in which rocks that are less dense than the subducting plate are scraped off and end up on another plate. The subduction of the Farallon plate also created the Cascade volcanoes that run from Northern California all the way to Washington. As the subducting plate descends into the asthenosphere, it melts and turns to magma, which then rises through the crust and forms volcanoes. The Cascade volcanoes are part of a large collection of plate boundaries known as the Ring of Fire. This runs along the west coast of North and South America, all the way to the east coast of Asia.
As Hannah mentioned earlier, tectonic plates are always moving due to convection currents, but these movements are not always uniform or even similar depending on their direction and speed. The average tectonic plate moves anywhere between 0.6 to 10 centimeters a year, with some outliers such as Hawaii moving up to 3 inches per year due to lots of tectonic plate movement and activity in the mantle, specifically the asthenosphere. The asthenosphere is the upper layer of the mantle where convection is thought to occur and is responsible for all plate movement. Plate movement can be measured through GPS and satellite camera monitoring of position change compared to an amount of time, giving us the unit centimeters per year that plate movement is generally measured by. The types of plates that are moved by these currents are continental and oceanic, with oceanic being denser due to their heavyweight rocks, and continental less so because of lightweight geological features. The North American plate, home to San Francisco, is classified as a continental plate, whereas our neighboring plate, the Pacific, is largely oceanic despite containing some parts of California's coast. These two plates meet at what we call a transform boundary, meaning that they are sliding against one another, causing the earthquakes we experience in the Bay Area and creating the San Andreas Fault, among others. Other types of plate boundaries include diverging, wherein two plates move away from one another, and converging, where they meet. While those do not specifically pertain to our own local fault, they were a big part of Pangaea's formation and subsequent breaking apart, as well as the creation and movement of all other continents on our Earth.
Now let's get into the history of some of the geological structures in California. Millions of years ago, the west coast of North America looked very different than it did today. The land that would one day be California consisted mostly of a large expanse of granite known as the Sierra Nevada batholith. This granite is about 120 to 85 million years old, during the Jurassic and Cretaceous periods. Today, the batholith measures 70 miles in width and 300 miles long. Over the millions of years, as the Farallon Plate subducted, the accreted rocks compressed against the batholith and created terranes.
This means that California is made of different terrains, packages of rocks enclosed within faults or boundaries that were created from the subduction of a plate, in our case, specifically the Farallon. Through that process, less dense rocks accreted onto the North American continent, aiding in the creation of an addition to our shoreline, resembling roof shingles in appearance. The terrains near the Sierra Nevadas are long and thin due to their old age and many years of compression, whereas those by San Francisco and the Bay Area are bigger patches because they are young and have not yet been compressed. Generally, these bigger patches are known as the melange, which means a mixture or medley, and they are very common in Marin County. All of these terrains had accreted onto the continent by the end of the Jurassic era, about 145 million years ago, while the oldest rocks were deposited during the Paleozoic. Also during the Jurassic Age, the first trench in California was created. A trench is a deep and very long depression between oceanic and continental land, created by subduction and the negative space therein. There were three major ones in California that we study today. The first, aforementioned one from 350 million years ago. Second, the Sierra Trench from 200 million years ago at the end of the Triassic era. And finally, the Franciscan Trench from 15 to 30 million years ago. All of these trenches were filled in with rock sediment over time, but were geologically impactful while they existed on the history and formation of California.
You may be wondering how the boundary along the North American plate changed from convergent to transform. About 15 to 30 million years ago, as the Farallon Plate was subducting, it stopped because of a mid-oceanic ridge. A mid-oceanic ridge is created when two plates diverge underwater and they create an opening in the crust, exposing the magma beneath it and allowing it to rise. Near Southern California, there was a mid-oceanic ridge on the Farallon Plate. This ridge was very large in size and was less dense than the Farallon Plate, so it would not subduct beneath the North American Plate. This then caused the Farallon Plate to stop subducting. However, the part of the plate ahead of the ridge kept moving until the plate broke. That break became what is now known as the San Andreas Fault. The San Andreas Fault is a transform boundary, also known as a strike-slip fault. When the fault was first created, it was about 60 miles south from its current position, closer to Los Angeles. Since its creation, the fault has been moving northwest due to the seafloor spreading on the East Pacific Rise.
Through accretion from the faults, San Francisco has a diverse population of rocks to be found within and out of the city itself. In the Bay Area, there are all types of rocks, including those that come from the three main families: sedimentary, igneous, and metamorphic. Sedimentary denotes a rock that was formed through sediment deposited through water or air, sediment being any solid material such as small particles of rock or mineral that is cemented through time or low pressure. Igneous rocks, on the other hand, are created via volcanic magma, either intrusive or extrusive. Intrusive meaning it cooled inside of the volcano and will often have crystals, while extrusive meaning the rock cooled outside of the volcano and will often have air bubbles. Lastly, metamorphic rocks are the results of other rocks that have been transformed by high heat and/or pressure. All of these are present in San Francisco as one or more of the rocks we saw in our field trips and in our studies. The first rock we saw in the Bay Area was called chert, a sedimentary rock formed in the bottom of the ocean. Chert is a pale greenish or orange and banded or layered in appearance, as is somewhat common in sedimentary rocks. Another common rock we came upon was granite, an igneous intrusive rock that is dark gray and often has multicolored crystals. Granite tends to appear often in the Bay Area because of the aforementioned Sierra Nevada batholith of granite. Thirdly, the most common sandstone we found was called greywacke, as it is formed in shallow areas of the ocean near land and is made of condensed sand, making it sedimentary. Greywacke and sandstone are, in the Bay Area, generally considered the same thing, as we don't have any other type of sandstone. This can be found on beaches like Rodeo Beach or Baker Beach in San Francisco, and is recognizable because of its gray or dull brown/yellow coloring and coarse-grained salt and pepper texture. The first igneous rock we encountered on our very first field trip was called basalt, specifically pillow basalt, as it forms in a knobbly pattern similar to that of stacked pillows. Basalt is formed near underwater volcanoes and is often dark gray and very fine-grained. It is extremely common because it makes up the majority of the ocean floor and therefore can be found there and occasionally on coastlines. Two rocks that stem from basalt as the original rock are greenstone and serpentine, both metamorphic rocks that have a greenish hue, hence the names. Greenstone refers to any igneous rock that has been metamorphized or taken on a green color because of present chemicals and metamorphosis, whereas serpentine is a rock defined by its extremely soft texture and once again color that is a further metamorphized version of greenstone. Lastly, we saw the sedimentary rock shale or oil shale in the Bay Area, specifically Point Reyes. Shale is formed near land in shallow water in between layers of rock and can be recognized by its soft texture and fine-grained, often gray appearance.
Let's take a look at San Francisco, beneath the thousands of buildings and homes. As you can see, there are many patches of land that are covered in different materials, such as sand dunes or rock deposits. You may also notice that these lines are dividing San Francisco into 5 different terrains. As we mentioned earlier, these were created through accretion. After comparing the data we had gathered from rocks in many different areas around the city, we found a pattern related to the strike and dip of the layers. The strike is the direction of the horizontal lines between the layers of a rock, and the dip is the angle of those layers. The chert in Gray Wacky and Billy Goat Hill dipped northwest. On Twin Peaks, we found chert that dipped north, and the Gray Wacky near the Art Institute dipped northwest as well. The rocks in all these locations were facing about the same direction, until we measured Gray Wacky on Nob Hill, and it was facing south. These arrows show how the layers in the area are dipping different directions, and that formed a valley. So as you can see, as the Farallon Plate accreted rocks like serpentine and chert, they were layered onto the continent like roof shingles to create the land we stand on today. In addition to our trips around the city, we traveled up to Point Reyes. On our way there, we got a look at some Gray Wacky and basalt. In Point Reyes, down by the beach, we found granodiorite, which is a type of granite that has large bands of crystal running through it. These are called dikes, and they are created when magma runs between the fractures of a rock and cools slower than the rock around it. Along this trip, we also got to see the past and potential effects of the San Andreas Fault. This diagram shows the west coast about 20 million years ago, and then 11 million years ago. As you can see, California, Oregon, and Washington are not quite the formation they are today. Over time, you can also notice that places like Los Angeles, Point Reyes, and San Francisco have moved northwest along with the San Andreas Fault. This picture is a forecast of what the West Coast could look like 10 million years from now. The San Andreas Fault will continue to move northwest, taking California with it, causing most of the state to be transferred to the Pacific Plate.
We never know what could happen in the next 10 million years.
But we do know that the Earth is forever changing.